Is this thing, it is on, okay. So let's remember again what our goal was, what we got to from yesterday. First, the broader goal, again, is that amplitudes are functions that only depend on kinematical variables. They don't know about the inside of the space-time and virtual particles and all the rest of it. They don't know any of that stuff. They only depend on the kinematical variables. And so our goal, what we're exploring, is if it's possible to just go to the space of the kinematical variables, no space-time, right? No Hilbert space, just the space of the kinematical variables, and in that space, find a question to ask, whose answer ends up being the amplitude, right? That's the very, very broad goal. Of course, we'd love to do it non-perturbatively, blah, blah, exactly, with gravity, everything in the real world, the standard model, and beyond. But we're talking about it in a very, very limited dB setting to begin with, of just this planar phi cube theory, this biadjoint phi cube theory. The advantage of this theory is at least at tree level, and we're doing it at tree level in perturbation theory. The advantage is that the singularity structure of these theories are universal, right? So at least at tree level, any theory has this kind of cubic, is given by these cubic diagrams. It has these kind of cubic diagram singularities. So, and it's, of course, it's relevant in some level to Higgs scattering, if you cared about that. Okay, so, okay, and so that's what we're doing. And what we've seen, as I mentioned, in the past sort of 10 years, is is that there's a kind of question that we end up asking. And the kind of question involves discovering some geometric structures that live in the kinematic space. Actually, it's relatively recent, in the past 2 years or so, that we've seen that these structures live directly in kinematical space. We've seen them live in auxiliary spaces before, but now we finally understand how to think and see them directly in kinematical space. And so these geometric structures, these positive geometries, in the examples that we're talking about, they're the most sort of simple version of positive geometries that are just good old-fashioned polytopes. There are some polytopes that live in kinematic space, and the amplitudes are associated with these canonical forms. So they're objects that have singularities, logarithmic singularities on and only on the boundaries of these objects. Okay, so that's the nature, the kind of answer that we're starting to see. So we have to figure out, where do these geometric objects come from? What kind of question brings these geometric objects to life? And then to find a way to find these canonical forms that are tied to them. Okay, so that's what we're trying to do. Now, last time we got to the point. Let me remind you that the kinematical space for this scalar theory are, if we have endpoint scattering, we draw this polygon where the edges of the polygon are the momenta. So we have pi up to pj minus 1. So our kinematical variables are these xij that are pi plus ... pj minus 1 squared. And there are n choose 2 minus n, which is n times n minus 3 over 2 of them, which are also a basis for all Mandelstam invariants, so that's very nice for n particle scattering. We already saw that a Feynman diagram, so each one of these xij's is one of the propagators that can occur in a planar ordered diagram. I remind you that when we've ordered the particles 1 through n around the circle, we also have a cyclic symmetry. We can just rotate all the indices by I goes to I plus 1, and the amplitude should remain invariant when we do that. Okay, but a particular Feynman diagram is associated with a triangulation of the polygon. Okay, so if I give you a triangulation, then on the one hand, this gives you a sequence of x's, the chords in the triangulation. And those chords are precisely the propagators that show up in a cubic diagram. And the cubic diagram is the dual of this picture. So the cubic diagram I would get in this case is, I put a point in the middle of all these faces. Okay? So planar, trivalent, planar cubic trivalent diagrams are dual to triangulations of a polygon. And each one of these propagators corresponds to one of the chords of the triangulation. And as we said, our formula for the amplitude, written in this way, the secret formula that we're supposed to get is given by the sum over all the triangulations, the product of all the chords in the triangulation, 1 over xij. Okay, so that's what we're aiming to get. Now, last time we got to the point of simply representing, so this is our kinematic space. Our space is the space of xij, and we have to find in the space of xij some question whose answer ends up being this guy. Okay? So as I've said a few times, that's a sort of nice thing about this business, is you begin with this very philosophical, airy-fairy seeming thing about trying to find some replacement, blah, 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 locality, unitarity, blah, blah, blah. But very quickly it turns into a concrete challenge. You want to find some way to produce this interesting function with poles. When the xij's goes to 0, they have to factorize on the poles. And we want to understand how we can do that without putting that in, right? And as we talked about, there's a clue that there's something going on by the fact that the pattern of the ways that these poles come together is non-trivial, right? That's locality. We know that the poles only come together in certain combinations. At 4 points, if I have a pole in the S channel, then there isn't also a pole in the T channel, right? At 5 points, if I have a pole when P1 plus P2, P1 plus P2 squared goes to 0, there isn't also a pole where P2 plus P3 squared goes to 0. We can't draw a diagram that has those two poles because our diagrams are local. So locality makes it impossible to have these overlapping channels. And the things that we're not allowed to do by locality are represented in that polygon by chords that cross. Okay, so if I have two chords that cross, those are two poles that cannot show up at the same time. Okay, so that's locality is the statement that the pattern of poles corresponds to triangulations of a polygon. No crossing chords are possible. Unitarity is the statement that already on one pole, the amplitude, the residue on the pole is supposed to factorize into 2. Okay, so locality and unitarity are very clean statements about this object, right? But as we said, the clue that there's something more is that if I just look at the pattern of all the poles that are allowed to occur together, it has this rich structure, right? Only some things are allowed to occur together, not others. And that rich structure is capturable by a polytope. And we showed some examples, right? We showed the example of an interval for 4 points, this pentagon for 5 points, and this cool-looking three-dimensional polytope, the three-dimensional isosahedron at 6 points. And as I stressed, the fact that the pattern of the poles that can occur together is polytopal is non-trivial, is really non-trivial. The fact that it's possible, for example, makes a prediction for, well, it tells you if you just count how many n poles, n minus 1 poles, n minus 2 poles, if you just count how many of these patterns you're allowed to have, that the alternating sum of these numbers has to add up to 0 or 2 to give you the Euler characteristic of a ball. And that's a very non-trivial fact, just about counting the graphs. Okay, so this is not an obvious fact. It's not obvious from Feynman diagrams. It's not obvious from any picture that we have. But it's a true fact, and as I stressed, it's a true fact that also explains factorization. Because these polytopes have the beautiful property that when you go to the face of the polytope, which corresponds to taking a boundary, which corresponds to taking a pole, right? A single pole is one of the faces, that the face looks like a direct product of lower polytopes of the same type. All right? So that is our goal now. Our goal in this lecture is to come up with a question in kinematic space where it becomes obvious that we have something polytopal that factorizes on the boundaries. That's what we're going to try to understand. Okay? And what we got to last time is this picture of just representing the kinematic space variables in this suggestive-looking picture. Okay, so we're going to simply this is just a picture that captures all the xij's. Remember, I should think about xii plus 1 as pi squared, which is 0. Okay, so the xii plus 1s are 0. But so here's how we're going to represent all the x's. So let me do a smallish example. Right, so we draw this right triangle, and here's just labeling the x's. So this is x13, x14, x15. This would be x16. So x16 is 0. I'll represent it by an open circle just to remind myself that it's 0. That's x16. So this here would be x12. Right? So this is just a direction where the j index increases. x12, 13, 14, 15, 16. It's just the dumbest grid. Okay? We're just putting these indices on a grid. But the next one here is x23, x24, x25, x26. Okay, so that's just a picture that represents all the variables. And it nicely covers all of them once and only once, right? And now, we talked about the fact last time that you can think of this picture as a chunk taken out of an infinite strip of the same type. Okay? And if I look at this infinite strip, then it keeps repeating. That's just the cyclic action, right? But it had this interesting feature that because xij is the same as xji, it had this Mobius identification, that a point over here, xt, which was ij, a point xt here, if this is ij, is identified with a point 1 minus x and 1 plus t over here, which turns out to be the point ji. And here, I'm just suggestively calling this t and this x. Purely suggestively, this is not our time and space. This is just some sort of funny notion of time and space in this abstract kinematic space, okay? But we also, last time, discussed something about why thinking about this time and space is useful, because of the following beautiful thing, that we know that there's going to end up being something important about whether chords of the polygon cross each other, right? So if I have ij and kl, we know there's something important about when the chords cross each other. And you see, what is this kinematic space doing? It's a completely trivial thing, but also a deep thing. When I draw the picture, when I'm thinking about this picture, the edges are associated with the particles individually, right? So the data is the momenta of the particles individually. The kinematic invariance involves the pairs of particles, right? So I'm somehow making something about statements of pairs of these guys, which I see here, right? I'm taking a pair of vertices here. So this picture is deceptively simple because you just think there's a polygon, but the variables are actually have to do with the pairs. Okay? So now you're just going to a space where the pairs are the points. Right? That's all we're doing. We're going to a space where the pairs are the points. But if we do that, then something beautiful happens, which is that two chords crossing acquires a causal interpretation. And that's what we said yesterday, that if I have this situation where ij crosses kl, then if this happens in this picture, it corresponds to the points ij and kl being the past and future corners of a causal diamond that fits inside this space-time. So that would be ij, this would be il, and this would be kj. Okay? That's cool. Right? So that's some little payoff of this picture that we translated crossing chords involving pairs to some relationship between the points. And the relationship between the points, if I think of this as time and this as space, is that they're causally, the past point can influence the future point. Okay, which means that there's a causal diamond that fits inside the space-time that connects the two of them together. Okay? If the points are not, if they're not crossing, then the points are either space-like separated, or, as we saw in examples, they're so far separated in time that the diamonds don't overlap. Okay, so these are the two ways in which the chords can be compatible and not cross. They can be like this, or they can be like that. Okay? All right. So that's our playground. This is our playground now, and we've seen that there is something sort of interesting about thinking about time and space in this funny kinematical space. All right. So, and as I also stressed, there's nothing sacrosanct about this picture. I could take any chunk out of this mesh that I liked, so long as it has this feature that it covers all the xij's once and only once. Okay, so I could also, for example, I could also have taken something that in the sort of continuum would look like a square. That would also work. If I did that in this picture, it would be something that looked, I'm sort of drawing it a little badly, like that. Okay, and I have to similarly make it jagged up there. Okay? But there are many ways of taking a chunk out of this picture that covers all the xij's once and only once. This is just one of the simplest ones, and we'll stick with it. It is, of course, amusing that the picture looks like the Penrose diagram of Minkowski space. And it looks like, I mean, just drawing it, it looks like I'm putting in x13, x14, x15 on the boundary, and I'm scattering them into the inside of the space-time, and something is coming out on the other end. And that's exactly the picture we're now going to develop. Okay? That's exactly the picture we're now going to develop. Okay, so what we now want to do is find a question to ask in this kinematic space. And as advertised last time, and some of the ringers in the audience, gave the answer anyway. Bad boy, right? What question are we going to ask? Well, we're going to just ask in this space-time, in this funny kinematical space-time, we're going to solve the wave equation. Okay. Now, so let's warm up a little bit and just remember some things about the wave equation in 1 + 1 dimensions. Okay? Because some things are a little bit cool about it. So independent of this setting, so here's time and space. So the wave equation is dt squared minus dx squared of something I'll call my wave capital X. And it's equal to, it can have a source. I'm going to call my source little c. Okay, so this depends on t and x. This depends on t and x. Okay, and now as usual, we like to introduce these variables. Sometimes people call them x plus minus. That's the obvious notation to use. I always get confused when there's plus minuses on the variables and also plus minuses in the formulas. So I like to use u and v instead. Okay, so u is t plus x over 2. V is t minus x over 2. I hope I have that 2 right. And then if we do that, then the wave equation just becomes du dv x equals c. Okay, so that's what we're trying to solve. Now, the normal way when you're like a kid learning about the wave equation in school or whatever, like we do in every physics problem, second order differential equation, you normally think about the initial value problem for the wave equation like we do for everything else. You have to give me, at some moment in time, x and the x dot. You have to give me x and x dot, and then I predict the future, right? All right, now there's something slightly cool, which is more natural to the Lorentzian problem. You can give, and I'll explain why in a second, but let's say I'm only interested in the solution of the wave equation inside a causal diamond. So in other words, I pick this point, I go out for some time here along a light ray, some other time along here a light ray, and I only want to know about the value of x inside this diamond. Okay? If I want to know the value of x everywhere, I have to tell you, if I want to know the value of x everywhere, I have to tell you what is x along this entire infinite slice. So I have to give you x at t equals 0 and little x, as well as x dot at t equals 0 and little x. Okay, that's the usual story. What if, though, I'm only interested in knowing what's going on in here? So clearly, by causality, I only need to know, and Lorentz invariance, of course, I only need to know about the value of x here. You give me the value of x here, and I don't need to know what's going on elsewhere, because they can't influence what's going on in there, right? But it's very slightly cool that all you need to know is the value of x on the boundary, and nothing about x dot. Okay, so it's a very tiny difference from the usual way we're used to thinking about the initial value problem. Okay? So you're allowed to just give the value of x on the light cone, nothing about the derivative, and it suffices to determine x everywhere inside. Okay? And let me explain why this is. And at the same time, we'll just solve the wave equation in complete generality. Of course, in this case, it's really trivial. But let me actually write down what the Gauss law is for the wave equation. You're used to the fact in even a fancier setting in electrodynamics that we have the normal Maxwell equation, or divergence of E is 0, or Laplacian of phi is 0. And then there's the Gauss law, which is the integral version of that tells you something about the integral on the surface of a sphere of E dot ds being the total charge inside. Right? So we want the analog of that for the wave equation. And the Gauss law for the wave equation is extremely simple and beautiful when applied to a causal diamond. Okay, so let's say you give me this causal diamond, and I give you the values of x here. This is x in the past corner of the diamond. This is x in the future corner of the diamond. This is x on the left side of the diamond, x on the right side of the diamond, and there's some charge density c inside there. Okay, so what is Gauss's law applied to this? Well, how do we get the Gauss law? In this case, it's really, really simple, right? All you do is you take the wave equation and you integrate it on the inside of this diamond, right? So on the right-hand side, you're just going to get the total charge. What are you going to get on the left-hand side? You're just integrating du dv, right? So the answer completely localizes on the corners of this diamond. Okay, so the Gauss law just tells you that x past plus x future minus x left minus x right is equal to the total charge inside the diamond. Okay? Is that clear? And as usual, as you're used to even from the ordinary Gauss law, you can think of this integral form as a sort of more fundamental one, if you like. Because if I just take that formula and I shrink the size of the diamond to 0, what do I get? I get the wave equation, right? Because that x past plus x future minus x left minus x right in the limit of the diamond, because infinitesimal, becomes nothing other than du dv. Exactly the double derivative. So this is the integral form. As I shrink the diamond to 0 size, it gives me back the wave equation itself. Okay? But now you see from this equation what I told you about how you solve in the initial value problem when the data is given on the corners of a light cone, of a causal diamond, it becomes trivial. So let's say you give me the values of x if I know what x is here, so let's call this x a of u on this side. And here I call it b of v. Here's some common value there, right? They're equal to each other there. Let me say I take a point here. I want to know what is x up here at u and v. Well, I plunk down this causal diamond, and I write down the formula. X at u and v plus this common value here. What should I call the common value? X naught. Let's call it here. Okay, plus x naught minus this corner, which is a of u, minus the other corner, b of v, is equal to the total charge c that's inside this diamond. So that allows me to solve for x of u and v everywhere inside. Okay? Is that clear? So again, it's very slightly cool that you just have to give just the data of x itself on the light-like boundary and nothing about the derivatives, and it suffices to determine everything inside. Okay. So that's one fact about the wave equation that we're going to need. Here's one more fact about the wave equation that we'll need in a bit. So we need the Gauss's law, and we need what I'd like to call the scrunch rule. Okay, and so this is the scrunch rule. Well, let's say you have some solution of the wave equation, but I want to take some 45-degree strip here, separated by two null rays at different times, and let's say out here the solution is x to the right, and here the solution is x to the left. Right? And there's something in the middle here, right? Given this solution to the wave equation, I can build another solution to the wave equation in a slightly different space, where I just get rid of everything in here. Okay, so I'm going to scrunch or collapse this region. Okay, so I'm going to imagine collapsing this region. So I'm going to scrunch this, and I'm going to be left with some kind of boundary between x right and x left. And now I claim this is a new space. This piece is missing, right? New space, but x right and x left are still a solution of the wave equation. Nothing has changed, but all the charge that I had in here, I have to add there as a delta function source at the juncture. Okay? And I think this is pretty obvious. How do we prove this? Well, again, by using Gauss's law. Everything is like you do in childhood electrostatics, except even simpler in 1 + 1 dimensions, because in 1 + 1 dimensions, in this Lorentzian problem, the Gauss law doesn't even involve an integral over anything. It just picks out the corners. Okay, so the Gauss law is even easier. So how do I do it? It's the usual sort of Gaussian pillbox type argument. Okay, so if I want to solve, if I only care about x to the right and left, well, this satisfies that this plus this minus that is this charge. Well, exactly the same formula is true here. Okay, all I have to do is make sure that the right-hand side is correct, and so I'll do that just by including whatever charge I had here as a delta function at the juncture. Okay. If you're given some solution to the wave equation, you can make new ones by taking various parallel regions and just scrunching them away. Okay. And you'll still get a solution to the wave equation. Okay, so those are the only things we need to know about the wave equation. So let's proceed. So now let's go back to our problem. So I now want to solve the wave equation in this geometry. Okay? So I want to solve du dv x equals c. But I'm now going to add one other ingredient. And here you might wonder why I'm doing this, right? So I'm going to say the word positivity. And I can't really justify it here without telling you more of a backstory. But the more of a backstory is in every other setting where this kind of thing happens, you go to some seemingly boring space of the kinematic space, nothing is going on, nothing exciting, n4 vectors, who cares? Then you say the word positivity in some appropriate way, and the magic starts. Okay, so you're sort of on the lookout for the fact that somewhere the structure that's needed is associated with the word positivity. All right? It's just in this case, it's so simple, I can just tell you what it is, and later we can bellyache about what it means and where it comes from, blah, blah, blah. Okay? But so I'm going to inject the word positivity here. And what positivity? Can I even spell positivity? Positivity. Okay. Well, what I mean by positivity is that I want x to be positive. Okay, so I want x to be positive everywhere inside. And I want the source to be positive. Okay, and now, we've already seen in our picture of the kinematic space that these edges are special. That here, I have to have x equals 0, and here I also have to have x equals 0. Okay? You remember that, right? We saw that in our example. So now what I want to do is solve the wave equation in this space-time, but demanding that x stays positive everywhere inside, so long as the source is positive. So imagine the source is fixed. Someone has handed me the source. And I want to figure out what I have to do to ensure that x stays positive everywhere inside. So once again, let's think for a moment about what solving for the wave equation inside here looks like. And by exactly the arguments that we just talked about, if I want to solve the wave equation in this space, it suffices to give as a boundary condition the values of x on this past light-like boundary. Okay, so if you give me x here, if you give me x here equals some a of u, let's say, I forget if this is a u variable, but whatever, you give me the x here, then given x there, I can solve for x everywhere inside. So as I said, the sort of analogy with something that looks like a scattering process is kind of interesting. You just give me the boundary values here, no derivatives, just the boundary values here, and then you solve for x everywhere inside. Let's just quickly see from Gauss's law why that's true. I mean, it's exactly the same argument. Let's just see it in this setting. Okay, so how do I see that if I have a point here, I can solve for it? So I claim that if I give you the value here, God, this red chalk sucks. Is there a what's wrong with this? There was a yellow chalk here at one point in time, but it's fine. It's fine. No, don't worry about it. I mean, I don't care so much that you can't see it. It actually physically hurts to use it. It like hurts my fingers. But I want to punish it back. You know that. All right. So if you give me x there, then how do I solve for it? Well, just plonk down the light rays. There we go. Okay? And so I have a Gauss's law that says, so let's call this point alpha and beta. That's 0 here, right? We have these boundary conditions. This is 0. So if I want to know x, then x plus alpha minus beta minus 0 equals the c. Okay? So that's how I can solve for x inside. Right? So all I need to do is give you the value of x at this past boundary, and I'm going to determine everything inside. All right? So now our new question is, what constraints do I have to put on the boundary value in the past to ensure that it stays positive everywhere inside? Okay, that's the problem we're now trying to solve. Obviously, it has to be positive. Positive has to go to 0 on one end and 0 on the other end. It has to be positive here. But it has to satisfy something else in order for the wave equation to give you an answer that stays positive everywhere inside. Okay? Now, this problem is still too hard, because I'm trying to find in the continuous space of all functions on the past, I draw any function I want. I want to know, is this one good or bad? Is this one, it has to be positive, right? So, over here, I would draw some function that looks like that. It has to start at 0, end at 0, stay positive everywhere inside. I draw this wiggly thing. Now, I take that wiggly thing, I shove it in, I solve everywhere inside. Does it stay positive everywhere inside or not? Right? That's what we're trying to figure out. So we're trying to figure out what are the constraints on this picture that I can draw such that it stays positive everywhere inside. And that problem is still too hard. It's very infinite. Okay? So let's make it simpler. Don't make fun of me. I mean, very, very infinite. It's a meaningful thing. You want me to be Cantor or something? Come on. You can make fun of me for that. But, there's interesting chalk here. I wonder if any of this chalk is better. There's green chalk, yellow chalk, purple chalk. All right, let's try the green and yellow. Huh? The pink chalk? Pink chalk? All right. There's 2 pink chalks. So, all right, yeah, very good. All right, so, okay, so what we're going to do instead is ask about the value of x on this boundary at a few finite places. Okay, so the dumbest thing we could do, which we should start with doing, is just ask, what can I say about the value of x? I won't keep coloring the blues and so on now. Okay, so just remember it's 0 here and 0 there. What can I say about x at this one point? So if I point here past 1, okay, clearly it makes sense to draw these light rays going into the space-time in and out. I have this point past 1, this point future 1. What can I say about the value of past 1 that guarantees that I stay positive everywhere inside? Okay, well, all I care about here is past 1 and future 1. I don't even care about any of the other points in here, right? So I know that I want past 1 to be greater than or equal to 0. But what is future 1? Now I can use the Gauss law to solve for future 1, right? I have to have that future past 1 plus future 1 minus 0 is equal to the total charge in here. So I'll call that C. Okay, so good. So I can solve for future 1 is equal to C minus past 1. But remember, I need future 1 to also be positive. I want it to stay positive everywhere. Okay, so I have the condition that past 1 is positive and also future 1 is positive, which says that C minus P1 is positive. Okay? So, what have I learned? I've learned that so if I plot in P1 space, I have to be bigger than 0. So this is where P1 goes to 0. But I have to be smaller than C, because this is where F1 goes to 0. Okay? And so P1 has got to be in this hot pink region. Right? Okay. So that's amusing. P1 has got to lie inside an interval. Okay? All right, now let's keep going to the next problem. Let's say I want to sample it at 2 places on the boundary. Yes?
It looks like that if you can take any point on that line and you can make all of this positive.
Sorry?
If you take various points, even,
Yes?
You can make it positive everywhere, right?
Well, no, you see, the value of what this thing is, first, it is positive everywhere. We know that it must be positive everywhere. We're putting in that it must be positive everywhere on the boundary. It has to go to 0 at the edges, right? But otherwise, it's got to be positive inside. But not everything that's positive is allowed. I mean, you see it already here, right? It could be positive, but I can't make it more positive than C. If I make it more positive than C, just at that point, then somewhere else it would have to be negative. Okay? That's what's interesting about this. It's kind of a global constraint, right? You're trying to put constraints on the initial data that satisfy some global property that everywhere inside it stays positive. And we're thinking about it from this global point of view now. And in fact, we're using Gauss's law to solve for things and so on, right? So I'm using Gauss's law as a shortcut. I'm not literally solving the wave equation in time from P1 to, I'm just using Gauss's law to write down the answer. I'm using this global perspective to, it's all trivial in this case, but I'm using this global perspective to write down the answer. But it's this global constraint of staying positive inside is enforcing some constraints on the boundary data. After we do all of this, we're going to come back to this local picture of time evolution. Okay, so we're going to reinterpret everything we do in that language as well. But for now, we're just going to do it in this sort of simplest way. All right, so let's go to the next case. Now I have 2 points, past 1 and past 2, and they go along with points future 1 and future 2. But now there's this interesting new point, I don't know, let's call it intermediate, on the inside. Okay? Once again, I want to imagine P1 and P2 are given, and I want to solve for all the other points on the inside. All right? So let's do it. I'm going to put some, let me call this C, C prime, and C double prime. Reason will become obvious in a moment. Okay, so C is just the total charge inside this diamond. C prime is the total charge inside this diamond, and C double prime is the total charge inside that diamond. Okay? So let's first compute F1. All right, so F1 is equal to, it's as before, is the total charge in this diamond minus P1. So that's C plus C prime minus P1. Okay, what about F2? F2, by this Gauss's law, F2 is C prime plus C double prime minus P2. Finally, what's I? I is that I plus P1, so let's write the Gauss's law, I plus P1 minus P2 is equal to C. P1 plus I minus P2 minus 0 is equal to C. So let me put I here. I is equal to C plus P2 minus P1. And I have to have, of course, I have to have that P1 and P2 are positive, but also that all of these guys are positive. Okay, so let's plot what this looks like.
What if we take P1 and P2 like close to each other and try to find out the identity which is...
Sorry?
But if we try to take P1 and P2 close by and try to find a local identity which will tell how the C's are related with the, the variation of P. That is, we are moving away from...
Well, but you see, so there's no constraints whatsoever on P1 and P2. The P's are just the boundary conditions in the past. You're allowed to give me any P1 and P2 that you like, so long as they're positive. We're asking that they're positive, okay? But you give me any P1 and P2 you like, and we're predicting the future. So there's no constraints on delta P. Okay? That's just the initial data, right? Okay, so let's plot what this looks like. Okay, so first we have to live, yes?
Then delta P would be somewhere related to the delta F, right? So
Yeah, so there's a formula that would tell you delta F in terms of delta P. You could try to take these things close. In fact, I'll say a little bit about, more about that later, okay? There's actually a very interesting, there's a very interesting question about how to think about the continuum limit of the polytopes that we're talking about. Okay, so I have to, P1 and P2 have got to be positive, so I have to be on this side. Now, what do I learn from the fact that F1 is positive? From the fact that F1 is positive, I know that P1 has got to be smaller than some C plus C prime. So here's some C plus C prime, and I have to be on this side. From the fact that F2 is positive, I learned that I have to be on this side, right? This is some C prime plus C double prime, right? So this is P1 positive, P2 positive, this positive, that's positive. Now finally, what do I learn from the fact that I is positive? Okay. Now you see, I have to have that P2 minus P1 is greater than minus C. Okay? And now the fact that the C's are positive really matters. Okay? Actually, it mattered even before. In my one-dimensional example, it mattered before that the C was positive. If it wasn't positive, I wouldn't have any interval at all, right? Because it was positive, I had an interval. Now it matters that all the C's are individually positive because this last requirement that I is positive is some other line in this picture, right? But whether or not you get a square or something else will depend. Is the line out here somewhere? In which case it's not imposing any extra constraints at all. Is it here somewhere? It would remove the entire space. Okay? But you'll notice that if I assume that all the C's are positive, crucially, this guy here is smaller than this guy there, C plus C prime, right? And what that means is that this last constraint is actually cutting that region out. So this point here is C. Down here would be negative C. Okay? So the fact that all the C's are positive is sort of crucial in telling you the shape of this region is actually fixed. If I didn't tell you anything about the C's, I wouldn't know about the shape ahead of time. If I tell you the C's are positive, the shape is fixed. And what is the shape? It's this beautiful pentagon. All right? So you should start seeing where this is going, right? So when we had n equals 4, just an interval. Right? When we have what corresponds to 5-point scattering, 2 points on the outside, we have a pentagon. Okay? Okay, so let's just keep going. One more example, and I won't draw the whole picture. Let's say we have 3 points here. All I want to do is do some counting here. So we have P1, P2, P3, some future 1, future 2, future 3, and let's just call them, I don't know, I prime, and I double prime. Not very imaginative, okay? Of course, I could label them in terms of the x's of the kinematic space, but here I'm just playing with solving the wave equation with these boundary conditions, okay? Now, how many variables do we have? We have variables that are P1, 2, 3, F1, 2, 3, I prime, and I double prime, okay? So we have 9 variables. And we have to ask if they're all greater than or equal to 0. Now, how many Gauss's law conditions do we have? Well, I have one mesh. Let me call this C1, C2, C3, C4, C5, C6. So I have 6 Gauss's law. That's good. That means that, that if you give me, given past 1, 2, 3, I can solve for the other 6 variables, f, 1, 2, 3, I prime, I double prime. And I can ask them to all be positive. So now what is this going to cut out? I begin life with the positive orthant, right, where P1, P2, P3 are positive. And then I'm cutting out 6 other hyperplanes. Once again, ahead of time, you don't know what the shape might look like, but precisely because all the C's are positive, you get a unique shape out of this. Okay? And the unique shape that you get is some shape with 9 faces, and it's exactly the 3-dimensional isosahedron. Okay? In fact, what you get here is the realization of the isosahedron, the specific realization of the isosahedron that we came up with a few years ago, where we didn't have this picture, okay, but the isosahedron is I can draw any way that I like, but I'm here and getting it in a very specific way. For example, here, this is not a random pentagon, right? This is a very specific pentagon where these sides are parallel, these sides are parallel, okay? It's a very specific pentagon coming from a very specific realization, right? Very specific set of equations cutting it out. And so we get this very specific realization of the isosahedron, of the 3-dimensional isosahedron in this case. That was a picture that I had up on the board yesterday that I didn't get to use yesterday, and I didn't redraw today, okay? But we drew, as I emphasized yesterday, there was a very specific 3-dimensional picture. It had all these sort of parallel sides and so on, and that's exactly the picture that you get from just asking for positivity in the wave equation here. Okay, so that's just observational. I'm telling you that this is where the isosahedron comes from. Okay? It comes from asking for solving the wave equation in kinematic space with positivity, asking everything to be positive on the inside. But why did it happen? So now I want to explain why it happened, right? Not just observe that it happens, but why does it happen? So in other words, now we're going to sort of reveal the real magic here, extremely simple, but the real magic, which is that we have a question, the simple question that we've asked in kinematic space. I hope it's now clear the answer to this question is built-in, manifestly polytopal, right? Because it's just defining a bunch of inequalities just by construction. Defining a bunch of inequalities, so this is, by construction, giving me something that looks like a polytope. But now I'm going to explain why this polytope is the magical property that when you go to the boundaries, it factorizes into 2 other polytopes of exactly the same type. So I'm now going to tell you where factorization comes from, how factorization is a consequence of this picture. All right, to do this, let's go back to just the sort of continuum picture. Sort of easier to say. I mean, it's exactly the same if I sample on discrete points, but it's actually funner to draw directly in the continuum. Let's go to this continuum picture. And let's say I want to go to a boundary. What does it mean to go to a boundary? It means that I've somehow arranged the initial data on the surface such that it's not true that x is literally positive everywhere. At one point on the inside, it's actually 0. Right? So that's the first boundary. Kind of first boundary would be that it actually vanishes at a point on the inside. Similarly, like these examples, right? In this pentagon example, I had 5 inequalities, but if I go to one of its boundaries, I saturate one of the inequalities. It should be positive, I said equal to 0, but only one of them. If I want to go to a higher codimension boundary, I put 2 of them to 0, 3 of them to 0, right? But if I want to see the first boundaries, I just put 1 of them to 0. Okay, and so the analog of that in the continuum is that I just want to choose one point in here, let's say here, and I want to say that at that point, x is 0. Okay? So at this point, star, I've put x star equals 0 here. Now what I want to know is what can I say about what the boundary values look like that are compatible with x star equal to 0? That's what I'm trying to figure out. When I'm trying to figure out what does a boundary look like, I'm trying to answer that question, right? Can I make a prediction? Do I somehow know what I have to say about the boundary values here in order to be compatible with x star equals 0? All right. Now comes the interesting point. Well, if you put x star equal to 0 somewhere, it's natural to ask, where else can you put it to 0? If you want to go to the next boundary, if you put x star to 0 here, what are the other places that you're allowed to put it to 0? Okay? And let me first tell you the answer. So again, with any of these points, you always shoot out the natural light rays. Okay? So if I shoot out the natural light rays from this point, this hot pink is really good. Thanks for the advice. Oh no, that's not. Oh, this is, sorry. Okay, if I put x star to 0, I cannot put x star to 0 in the shaded region. That's where I cannot put it to 0. In other words, I can't put x star to 0 in any region which has a causal influence on x star. Why is that? Well, let's go back to our Gauss's law. So this is the fundamental point. So I have this point x past, x future, x left, and x right, which are space-like separated. And I had the Gauss's law, x past plus x future minus x left minus x right equals c. And the point is, let's say I put the point x past to 0. I can then not also set x future to 0. I can't do that. Because if I do that, I would put both of these terms to 0. The x's are supposed to be positive, so it would have 2 negative numbers adding up to a positive number. Okay? So it's impossible. So positivity and the causal structure make it impossible to set 2 points that are the past and future corners of a causal diamond to 0 at the same time. Okay? Yes? Sorry? They can... Well, first of all, they can't all be 0 because if I have these positive sources, I can't solve the wave equation with every one 0. Okay? And secondly, we're just trying to figure out, so they can't. I'm assuming that these constants are all positive. Okay? So that these, Okay, so if you then put x star to 0 and you ask where in this space-time are the points that are the future and past corners of a causal diamond relative to x star, it's everything in these shaded regions. Okay? Is that clear? So I can't put x star to 0 anywhere in there. All right, let me go back to this picture. I'll draw it again. Okay. Furthermore, so I can't ever set x star to 0 there. So at some level, I care less about what's inside here, right? But in a more specific level, I care less about what is inside there, because so long as I know the value of x, like let's say I know the value of x everywhere on this boundary, then I know I can compute everything in there, right? Similarly, if I know the value of x on this boundary, I can compute everything in here. So simply from the knowledge, so I don't need to know anything about the x's inside this shaded region. I can't set them to 0, and just by knowledge of the value of the x's on the boundaries, I can reconstruct what the x's were inside if I cared, if I wanted them. Okay? Yes?
So I have a confusion. You can't set x to 0 just inside or also on the bottom? Because on the vertical line...
Yeah, sorry. The x is 0 here, exactly. So x is 0 on the boundaries. Now I'm trying to put a point in the interior to 0, to go to a boundary. Okay? To go to a boundary in the space of solutions, right? So as I move the external things around, somewhere I might hit a place where I put an x star to 0 in there. And now I want to know, having done that, where else might x go to 0 on the inside? What might correspond to another boundary? Okay? That's right.
In the shaded region,
yes.
also the borders of the shaded region?
No, the borders, here you'll have 0, yes. But here it cannot be 0. Yes, that's right. Yeah. That's right. Yeah, here I have a boundary condition on the left here. That's right. Yeah. Yeah. Right. But that's literally talking about one point there, right? Yeah, that's right. Yeah, that's right. So we have these boundary conditions there. Okay. Now, so we don't need anything about these regions. We can reconstruct everything about them given the knowledge of the things outside. So now, in other words, the answer for solving the wave equation for this full problem can be completely reconstructed without any loss of information by scrunching this region away and scrunching that region away. Okay? Now what do I get when I scrunch those two regions away? Well, I have this triangle here. Let me draw the picture. Let's start this picture. So when I scrunch this region away, I move this triangle down here, right? I have to include whatever source there was there as a delta function. Okay, that's some positive source. I don't care. Everything is positive anyway. So I get some extra positive source here. And now this blue line has moved down here. Similarly, when I scrunch this triangle, I get a delta function source here, and I get the blue line up there. All right? Now, all of the boundary values that I had here, all the boundary values that I had here before, the ones that I care about, that I can reconstruct everything else from, are here and there. So here they are. They're here and there. And so what I need to do is solve this new problem with the boundary values here and the boundary values there, positive sources. I just changed the positive source a little bit. Still a positive source in this problem. But what is this problem? It's two copies of the problem for the triangles that we've solved already. See, this is our triangle. 0 there, positive everywhere inside. And this is independently a different triangle. 0 here, 0 there, positive inside. Okay? So that's the origin of factorization. We've learned that the set of all the solutions of the wave equation, which are 0 at one point here, is given by the direct product of similar wave equation problems for smaller triangles. Okay. Isn't that amazing? Okay, so that's factorization. That's the origin of factorization. So now we see that whatever object we have, and now I can sample it on finitely many points if I want, right? If I sample on finitely many points, I get some finite polytope. But this explains why I get a polytope, A, but B, why the polytope has a property that when I go to the boundaries, on the boundary, what the face looks like is a direct product of two lower polytopes. Even tells me which two lower polytopes by precisely which triangles I got. Okay? And so that has accomplished what we wanted to see. We asked a question in kinematic space, and this question both yields a polytope and explains where factorization comes from. Whereas the usual Feynman diagram picture only makes factorization manifest, and the fact that it's polytopal is not manifest. Okay, any questions about this? Yes?
You said it was not to go and solve wave equation in this field, but how do you actually get it?
Yeah, no, at the level of what I've told you, nothing. You just do it. Yeah. I would have to tell you more about why this x plus x minus x minus x structure is natural. Okay? But at the moment, I can't tell you anything. We're just doing it. We do it, it looks physical. These are totally bullshit words, okay? But it looks like a physical, simple, natural thing to do. Okay? Again, we're sort of motivated by the fact that when we drew, the 0th order starting point was totally natural, right? Just drawing the variables. They're on this grid. The fact that the xi plus 1s are 0 gives you not an infinite thing, but it gives you a strip. Okay? And so far, so good. Then there's this observation that the crossing of chords has a causal interpretation, if you think of this as time and space. All right? Once you have that, you ask a dynamical question in the space, and off you go. Where this kind of thing has more teeth is if you say, what would happen if I added interactions in this picture? Does that mean something? You can sort of go on to see that. And so I don't have an answer to those questions yet. But yeah, at the moment, I haven't told you, I haven't given you a deeper reason for it. Maybe the students can totally ignore these words, but I'm telling you a story about how to think about something in this sort of very simple physical way. But there's an inverse of this story that there's a natural way to get these polytopes to begin with that's associated with these things called cluster algebras. And in a sense, I'm giving you a way of thinking about these cluster algebra polytopes where you don't need to know anything about cluster algebras, you just play with the wave equation and so on. But if you want to ask your sort of question, where do these things come from? Well, then knowing about the cluster algebras helps, and it gives you a sort of a reason for where these things come from. Although it didn't, it took some work to see that this is the natural way of thinking about the polytopes from the point of view of the cluster algebra. So the physical picture is always useful. Okay?
So this structure is in a single Feynman diagram, or is it?
No, the sum of all the Feynman diagrams, of course. Yeah, no, that's the point. Now we're not seeing what we're doing. Well, now let's talk about what the amplitude is, right? So far I've just talked about geometry. We want the kinematic space. We solve the wave equation in kinematic space. We find this region associated with it. And so this is the procedure that I've told you, right? In kinematic space, you see a geometric structure. And now we see how you see the geometric structure. You have to ask some kind of question, and then in kinematic space, and you get this object. Now I can finally tell you what is the amplitude. So what is the amplitude? What is the question that the answer is the amplitude? And so we have the scattering form and amplitude. Okay, so let's return to this picture. And imagine I'm picking some fixed n for particle scattering, right? So for fixed n particles, that means that in this picture I have to plunk down, let's say I'm doing n equals 6. Now I'll label it the way we talked about. So this would be 1, 3, 1, 4, 1, 5, 2, 4, 2, 5, 3, 5, 3, 6, 4, 6. Okay? So here are the points that I care about. Okay, so here's the claim. We say that on this space, on X space, on Xij space, there is a form omega which is not a top form. Okay? So that's the amusing thing. We have like 3 propagators at 6 points, even though we have 9 variables. Right? So I'm looking for a 3 form. There is an n minus 3 form on this large dimensional space. Okay, there's an n minus 3 form, omega, on Xij space. N minus 3 is, remember, for 4-point scattering, we had 1 pole. 5-point, we have 2 poles, right? So for n particle scattering, we have n minus 3 poles. So there's some n minus 3 differential form that lives on Xij space. So far, this is an n minus 3 form in a very high dimensional space. And what we learned in the earlier lectures is that once you get polytopes, you get forms associated with them, canonical forms associated with polytopes, which have the property of having logarithmic singularities on and only on the boundaries of the polytope. But that's not what we have here. We have an n minus 3 form living in this very high dimensional space. So what I need to do is find a subspace on which I can evaluate this form. I want to pull back this form to a subspace, where on the subspace is just n minus 3 dimensional. Okay, so what is that subspace here for us? It's a solution of the wave equation. So I take this form, omega, and I pull it back to the solution of the wave equation. Just like we did, right? Even in this discrete case, we solved x plus x minus x equals c, x plus x minus c, right? So that gives me just some linear subspace. That's the plane, right? So in this big dimensional space, I have an n minus 3 dimensional plane. And now, on the one hand, what happens when I look on that n minus 3 dimensional subspace? What do I see on that n minus 3 dimensional subspace? I see the icosahedron. That's just what we did, right? So we just discovered with these positives, a positive solution of the wave equation, sorry. A positive solution of wave equation. And this form needs to have the property that when you pull it back to the subspace, it becomes the canonical form on the subspace of the corresponding icosahedron. That's it. So that's the question finally in kinematic space that's now giving us an answer, which is a form. Okay? And finally, the amplitude itself, when I pull back to this subspace, this form is some universal top form, so some universal dn minus 3x, I'll be a little loose here, multiplied by the actual amplitude. That depends on the x's. Okay, so let's see how this works in examples. I'll just do it in the, shit, once again. And this uniquely fixes omega. Okay, so this omega is uniquely fixed by this. Okay, so here's an example. Let's do n equals 4. Our variables are s and t. We can think of them as x13, that's s, x24, that's t. And so the space is this big two-dimensional space, right? And I have a form that lives in, it's an n minus 3 equals 1 form that lives on x13, x24 space. Okay? Now, I have to find the form that has the property that when I pull it back to the solution of the wave equation, I get the canonical form for the icosahedron. What is the solution to the wave equation in this case? The wave equation in this case was simply x13 plus x24 equals c. Right? That was our first simplest example, where if I now use this notation, this would be x13 and this would be x24. Okay, so it's x13 plus x24 equals c. And if we look at the positive subspace, which was x13 positive and x24 positive and c positive, well, what is that here? Well, we did it already, right? If I now draw it in this bigger space, that's this line. If that's this line, this is a line x13 plus x24 equals constant, where the constant is positive, and I'm intersecting it with this positive quadrant. Okay, so in other words, the subspace in this case is this interval. This is a slightly more invariant way of doing it than we described before, right? When we were talking about before, we said, imagine you gave me the past data, and then I'll solve for everyone in the future, and then I plotted what it looked like in P1 space, right? But slightly more invariantly, there's just some n minus 3 plane that lives in the space of all the variables. Okay? And I'm just intersecting that n minus 3 plane with the positive orthant, where all the x's are positive. Okay, so this one-dimensional line, this is the whole line. If you like, the whole line is a solution to the wave equation. This is the positive solution of the wave equation. Okay? It's positive in here. But I have to find a one form on the whole space that when I pull it back to the subspace, it becomes the canonical form for the icosahedron, which is just the interval in this case. Okay? And so what is that one form? Well, we wrote it down already, but this one form is dx13 over x13 minus dx24 over x24. Minus sign is important. Okay, so, but how do we see that this becomes the canonical form for the icosahedron there? Well, let's pull this back to this subspace. We did this exercise already a few lectures ago, but now let's sort of interpret it in this language. Just do it again. Okay, if I pull this form to this subspace, what do I get? So if I take omega 1 and I pull it back to the wave equation subspace, this is dx13 over x13. Well, then I have dx13 plus dx24 equals 0. So this form becomes dx13, let's say, which I can pull out, 1 over x13 plus 1 over x24. Of course, on the subspace, x24 is given by c minus x13. So on any fixed subspace, there's a relation between all the x's. But finally, the point is that this has to be true on any subspace. So I can wiggle this around. They have to be positive, but that doesn't matter. I mean, I get a smooth variation of every possible set of x's that I can get in some open positive region, but that's trivially enough to fix what it is everywhere. Okay, so that's why I'm sloppily writing this down just as 1 over x24. On this subspace, x24 is not independent of x13. It's given by c minus x13. Okay? But, oh, sorry, I should have first paused. So clearly, this form is the canonical form for this interval. Right? It would be dx13. Let's write it again. 1 over x13 plus 1 over c minus x13. Right? In the language that we wrote in the early lectures, I could put a minus sign, 1 over x13 minus 1 over x13 minus c. Okay? So this is indeed the canonical form for an interval. It has a logarithmic singularity at x13 equals 0, has a logarithmic singularity at x13 equals c, which is where x24 goes to 0, and no singularity at infinity. Okay? As I stressed before, the fact that there's no singularity at infinity is the projective invariance of this form. Okay? The form is projectively invariant, and so that means that it doesn't have any singularities at infinity. Everything only depends on ratios of the x's. However, term by term, one Feynman diagram, in this case just the S channel, would give me dx13 over x13. That one does have a singularity at infinity. This one does have a singularity at infinity, but they cancel in the sum. If you want to think about even this simple partial fraction formula in the language of the triangulations of simple polytopes that I was talking about before, this is such a simple example, but we can do it. Remember, I told you that every time you have a simple polytope, you can always triangulate it by going to the vertex and writing down, by sort of plunking down a point and triangulating with respect to that point, right? So in this case, just on the interval, just in one dimension, what is this triangulation of the interval? I would put some point out here, star, maybe at infinity, and the triangulation is to say that it's this minus that. A minus B. Okay? Partial fractions is exactly that formula. Just saying it's A minus B, where you send B to infinity. So when you literally do partial fractions, you send B to infinity so you don't see that pole. In this formula, you'd send C to infinity if you do partial fractions, so you wouldn't see that, the analog, you wouldn't see the second pole, but there's a pole at infinity. Okay? So that's what we're doing. The Feynman diagram is triangulating this interval. How stupid, right? It's triangulating this interval with one piece at a vertex and another piece at infinity. So that term isn't projectively invariant. That term isn't projectively invariant. And that's why there's two channels. Whereas the actual answer is just the canonical form for this interval, which is really one term. It's just d log of x13 over x24. Okay? And this is the most trivial case, but of course it keeps on going as we go to higher points. As we go to higher points, we would now have to figure out, let's say I want to do n equals 5, any n, right? The first nice obvious point from the wave equation, I mean, I just declared that we got the isosahedron, but let's just go through it slightly, just very slightly more slowly again, why we got the isosahedron. We saw that I can put one x to 0. Let's say I can do it in the discrete, right? How do I see that the vertices of whatever this polytope that I'm getting is correspond to triangulations of a polygon? How do I say the vertices correspond to Feynman diagrams? Well, it's very easy. It's just repeating things we've said, just to flesh it out a little bit more. So let's say I take this picture, n equals 6. And let me go back here and draw the corresponding polygon. So I put x to 0 somewhere in here. I know that that corresponds to putting one of these chords to 0. Right? I know I have a polytope, manifestly, from the left-hand side. I know putting something to 0 here means I put one of the chords here to 0. But then I know from that picture that I can't, who else I can't put to 0. The ones that I can't put to 0 are the chords that cross this. The ones that I can put to 0 are the other ones. So what is another one that I can put to 0? Well, maybe that one. What is another one that I can put to 0? Maybe that one. And then I'm done. I can't put anything to 0 anymore. Okay, and so you see every pattern of interior points that I can put to 0, finally going to a vertex of the polytope, is associated with some triangulation of the polygon. Okay, so this gives us a sort of conceptual understanding for why triangulations of the polygon could end up as vertices of a polytope. I just built the polytope, and then it's just manifest from the consequence of this positive wave equation picture, that all of the vertices, I put one face to 0, then another one to get an edge, another one, finally I go down to vertices. Every vertex is associated with triangulations of the polygon, in turn dual to cubic diagrams. Okay, so I learned from that this wave equation, positive wave equation polytope, is a polytope whose vertices are triangulations of a polygon. I also notice that every vertex I can only put n things to 0 to get there. So this is a simple polytope. And since it's a simple polytope, that was one of the cases we talked about last time, there is one very simple triangulation of it. Go to every vertex and write down the d log of all the variables that end on that, of all the face variables that meet at that vertex, and sum over all vertices. One of many triangulations, and as we've stressed, one that term by term hides a symmetry of the answer, because every term also has some poles at infinity that cancel out only when you sum over everybody. Okay? But nonetheless, that's a triangulation of the answer. It's given as a sum over vertices, and since every vertex corresponds to a triangulation of a polygon or a Feynman diagram, this expansion of the form is known as Feynman diagrams. Okay, so we see how Feynman diagrams emerge as one way of computing the canonical form for the isosahedron. But there are many other ways of triangulating the isosahedron. And I won't spend time to actually go through a number of the detailed examples, but they're written down in some of the papers, and more papers will come out soon. But there are concrete new recursion relations, for example, that you can get to get the amplitudes of this phi-cube theory way faster than Feynman diagrams. That's the big surprise that I mentioned already a few times earlier. I never thought that there was anything new or simple to be known about stupid scalar theories, but stupid scalar theories have a hidden symmetry. And that hidden symmetry is associated with a polytope. And that's associated with faster formulas for them than Feynman diagrams, even for stupid scalar theories. Okay? And you really see it on the computer. You really, really see it. You want the 25-point answer, you hit Shift-Enter with Feynman diagrams and with recursion relations, and you'll see orders of magnitude difference in how quickly you get the actual numerical answer. Okay? So this is not a question of just, I like to tell especially students, when you're working on physics, make sure you're writing down new formulas. If you're not writing down new formulas, there's a very good chance that you're not doing anything interesting. You're just deriving things, moving things around. This is the same as that, very elegant. But when you know the answer already ahead of time, that's not so exciting, right? It's important to work on a problem that forces you to write down a new formula. And if you're writing down a new formula, you can be guaranteed that you're doing something of worth, okay? So there are new formulas here. I'm not writing them down for you, but I promise you that they're new formulas. It's not just reinterpreting something to get Feynman diagrams in some complicated way. Okay? So, and again, I stress that the Feynman diagrams are a very natural way of getting the form, but they have this peculiar feature that they break the symmetry term by term. And this is the point I wanted to say. Not only is it true that you restore the symmetry when you add all the Feynman diagrams, it is also true that you cannot restore the symmetry unless you add all the Feynman diagrams. You can't take any subset of them with any signs you want. There's nothing you can do to get the answer projectively invariant unless you add all of them up together. Okay? Now, this is something somewhat similar to things that have been seen in the context of n equals 4 super Yang-Mills. There's a very similar hidden symmetry known as dual conformal invariance, and that also has consequences. It tells you that if you go off to infinity in a certain direction in momentum space, the amplitude dies, even though term by term in Feynman diagrams it blows up. Okay, so it's a surprising fact that the amplitude dies. You have various indirect reasons that you can sort of, with some work, prove that it dies, but the conceptual reason we understand that it dies is that actually n equals 4 super Yang-Mills has this interesting conformal symmetry in momentum space. And you know, the exciting thing about conformal symmetry is inversions. It allows you to invert x to 1 over x, or x to x over x squared. So when you have a conformal symmetry in momentum space, it allows you to invert p to 1 over p, roughly. So that means that infinite momentum is not a special place. That's why you can't have any singularities at infinite momentum. Okay? And so that's the sort of conceptual reason why there's no poles at infinity. There's no bad behavior in the Yang-Mills amplitudes as you go off to infinity in particular directions. Okay, so that's a hidden symmetry. It's not there term by term in the Feynman diagrams. It's there in the sum of all the diagrams. And because it's there, because the pole at infinity cancels, that's the magic that allows these famous recursion relations, like the BCFW recursion relations, to work. Okay, the method of deriving recursion relations by itself is just Cauchy's theorem. There's nothing deep about it. The deep part is that the amplitudes have a property that's not obvious in Feynman diagrams. They vanish at infinity in some interesting way that's not obvious term by term, which is ultimately related to this hidden dual conformal symmetry. Okay? Well, we have something similar here. The amplitudes actually have no pole at infinity. Now, this is an exercise that you can do. We can actually see it. The simplest case is a little trivial, but it still shows what's going on. You see, these amplitudes, I write down 1 over s plus 1 over t, and what do you think, what would you roughly expect as the behavior of this amplitude as you go off to infinity in Mandelstam space? It goes like 1 over energy squared, right? So that's your expectation. Off you go, it goes like 1 over energy squared. Now, what this picture is telling you is that there's no pole at infinity, and that means that if you go on these subspaces, there should be no pole at infinity. That's actually going to predict that the amplitude falls off faster than 1 over energy squared in some direction. Which direction? Well, I have to pull back to the subspace to see the direction. And let's see why it works. It's because this is equal to s plus t over st. And now remember that my subspace is s plus t equals constant. Okay? So if I sit on the subspace where s plus t equals constant, then on that subspace, if I go to infinity, the amplitude actually goes like 1 over s squared. Okay, even though generically it goes like 1 over s, there's this sort of cool place that you can go to, very trivial in this example, okay, but still, there's this place you can go to where it actually dies faster than you would naively expect, and also faster than you get term by term from Feynman diagrams. Okay? Doesn't matter whether you go to the subspace or not, the 1 over s goes like 1 over s, 1 over t goes like 1 over t, but on this subspace, the sum of them goes faster, goes like 1 over s squared. Okay, so this is the consequence that this hidden symmetry has. There's interesting subspaces where when we go to infinity, the amplitude dies faster than you would naively expect. Exactly the same as the fact that dual conformal invariance in n equals 4 super Yang-Mills implies that, or even for ordinary gluon scattering at tree level, it implies that that gluon amplitudes, when you go to infinity in a particular direction, die faster than you expect term by term from Feynman diagrams. Okay? So this projective invariance of the scattering form, which is made manifest by the fact that the scattering form is the canonical form of this wave equation associahedron polytope. And so this picture in kinematic space makes it totally manifest, totally obvious. That's a symmetry that's not seen term by term. It's a property of the answer, and allows recursion relations that get the answer faster. They're not BCFW. They're another recursion relation that's made obvious by this picture. Okay? And the analog of all of this for n equals 4 super Yang-Mills is the amplituhedron. So now in n equals 4 super Yang-Mills, you have a different story. The external kinematical data is not represented by Mandelstam invariance. It's just directly represented by the momenta of the particles, the null momenta of the particles. There's a better way of representing them in terms of the so-called momentum twister variables associated with the external particles, but this is not very fancy stuff. It's just a simple algebraic relation between ordinary momentum variables, spinor helicity variables, and these momentum twister variables. But in the end, every external particle is associated with a 4 vector, just a 4 vector. And now your kinematic space is a space of n 4 vectors. That's it. And now you have the analogous question. What are you going to do to ask in the space of n 4 vectors whose answer gives you all the richness and complexity of scattering amplitudes? And there's an analog of all of this, okay? Except it's both simpler and more sophisticated. Okay? So it's simpler because what the space is has none of this extra bells and whistles, wave equation, these physical sounding words. There's extremely little that you can do in this space. Extremely little that you can do. And what you can do, and then you add the word, what you can do is essentially topological. You can basically only ask topological questions in this space. But they have the following flavor. So instead of, let me not tell it to you for 4-dimensional vectors, it's a little harder to visualize. There's a story of the amplitude when the kinematical space is m-dimensional vectors for any m. Okay, so m equals 4 is what you care about for n equals 4 superambials. But you can ask it for m equals 2. Okay, so imagine that you cared about your kinematic space is the space of n 2 vectors. Okay, so here is 1, 2, 3, 4. I have a bunch of 2 vectors. Now, in this space, I have to ask some interesting question. And the only structure that we have is that there's an ordering for them, just like we have here, because there's some sort of color ordering in the underlying amplitude. So they're ordered, 1, then 2, then 3. We have an ordering for them. Okay? Once you have an ordering for them, you can do the following thing. So now I'm just giving you a cartoon for what the amplituhedron looks like for n equals 4 super-Yang mills. Having seen this, I just want you to have some idea of what the story is for gluons. And we'll end soon. I'm not gonna prevent you from. I just want to give you a cartoon. So now the kinematical space is the space of n m-dimensional vectors. So you can just call them. You can group them in a matrix, an m by n matrix, Z1 through Zn, where there's m of these, where this is m-dimensional, and there's n of them. And now let's look at the case m equals 2. You have the case m equals 2. So here's a vector, here's another vector, some vectors. There's just a bunch of 2 vectors. This is my space. But I have an ordering, 1, 2, up to n. Okay? And in this space, you have to ask a question. So here you see, here we first found some kind of, there's a positive region, right? There's some interesting positive region. And the positive region here was just asking all the x's are positive. Then there was a subspace. And the subspace was solving the wave equation. Okay? And so the icosahedron, the positive geometry, was the intersection. So if I say this sort of very, very impressionistically, we had a positive part where all the x's were positive. We had a subspace which solved the wave equation. This was an n-3-dimensional subspace. So this is kinematic space. This was the space of all xij's. The positive part is just the orthant. I'm drawing it like a ball for no reason, right? There's just some region in xij space. Okay? In this case, it was just the orthant. There was a subspace which solved the wave equation, and the intersection for appropriately positive subspace. So the sources have to be positive as well. So the subspace had some positivity condition on it too. But I have the positive part, I have a positive subspace, and the intersection of the subspace with the positive part gave me the icosahedron. Okay, so that was our picture. Exactly the same picture is true for the amplituhedron and for n equals 4 super-Yang mills. Exactly the same thing is true. And I just want to give you a cartoon for what it's like. So we just talked about what the space is. So now I have my kinematic space is the space of m, n, m vectors. So to give me a point in the space, you just have to give me this n by m matrix. N by n matrix. So this is my kinematic space. This is my kinematic space. And it's exactly the same thing. First, I have to find a positive part. So of all the possible collections of z's you can have, there's some positive part that we're going to declare we like. Okay? Next, I have to find a subspace of the appropriate dimensionality. And when I intersect the subspace with a positive part, I get a positive geometry. In this case, it's the amplituhedron. And I'm drawing it curvy because this is no longer a polytope. Okay? This is not cut out by linear equations, no longer a polytope. It's a much more non-linear object. Okay, but just to give you a flavor, what is the positive part? What is the positive part? See, now when I'm scattering gluons, my data is that I have n gluons, but there's some more data. The gluons have helicity. Okay? So, and a very important variable is k, which is the number which have positive helicity, have negative helicity. In fact, conventionally speaking, this k is the number that have negative helicity minus 2. Okay? So the amplitude vanishes if everyone has positive helicity or everyone but one has positive helicity. So the simplest case is where two of them have negative helicity, and that we call conventionally k equals 0. The next one is k equals 1, and so on. So there's this one extra integer that's k. See, that's an example of something we didn't have in our phi cube problem. We didn't have anything like helicity, no spin, no k. Right? So this amplituhedron is now going to depend on the external data, n and k. So let me tell you what it looks like. Again, in the case of n equals 2, first I have to tell you what the positive part is. So P simply asks that all of these two-dimensional vectors, let me just draw the tips of the vectors. Okay, if I just draw the tips of the vectors, there's 1, 2, 3, 4, and so on. It just says that all the arrows from one to the next, they're all winding around in the same direction. Okay? So it says that the I plus 1 are all pointing in the same, are all winding in the same direction. If I say it in the actual language of the vectors, it simply means that this little determinant, I, zi plus 1, is positive, right? So this is for n equals 2. My kinematic space is just 2 by n matrix. And first, I have to demand that everything is winding around in the same way. But what's the meaning of k? Okay? They have to wind around the same way. First, and there's also a topological condition that the winding number of this path, 1 to 2, 2 to 3, 3 to 4, around the origin, this winding number has got to be given by k. Right? In fact, in slightly more detail, it's k minus 1 over 2, the floor of k minus 1 over 2. But anyway, it's basically given by k. All right? So that's it. In this space of n two-dimensional vectors, there's a positive part where everything is winding around the same way, and then you have to specify how much it's winding. Okay? And the winding number tells you what the k is. So that's the positive part. And now there's a family of subspaces. I don't think I'll describe what the subspaces look like. It would take me another 5 minutes, but we want to go to lunch. There's a family of subspaces, though. Okay, and if you now just but it's also given by, well, let me just write it down. Okay? Just so you see, it's not remotely as complicated as the wave equation. Okay? The family of subspaces is simply the following. I'm going to take a given point. So let's say I have this Z. Alpha runs from 1 to 2. ZAI. A runs from 1 to n for all the particles. I runs from 1 to 2, because they're just these two-dimensional vectors. So my subspace is just this linear subspace. I start with some fixed Z star, and I translate in the direction of some fixed k-plane in n dimensions. So I write it like this, plus some y alpha, some y I delta alpha A. Okay? Some yi alpha delta alpha A, where alpha runs from 1 to k. What this is doing is, if you imagine that sort of Z is a point, I'm just translating Z in the direction of a k-plane delta. So this is some initial point Z star, and this is translating in the direction of a k-plane delta. So this is a picture in n dimensions, where n is a number of particles. Okay, but I start with this particular plane given by the z's, and then I'm translating the whole plane in the direction of another one. It's just a linear subspace in all of Z space. So you see there's no dynamics, time, x plus x minus x minus x. They're just totally primitive linear algebraic constructions, because we have nothing else at our disposal. Okay? This is just a space of n z's. Nothing else at our disposal. We just had an ordering, and that allowed us to say the word positivity. Okay? And then, so that's our positive space. That's our subspace. And the claim is that if you intersect that subspace with the positive part, you get a pretty fancy positive geometry. Okay? And the canonical form of that positive geometry is actually related to amplitudes. In fact, this one turns out to compute one loop amplitudes in n equals 4 super Yang-Mills, kind of accidentally. If you want, but literally directly tree amplitudes in n equals 4 super Yang-Mills are this story with n equals 4. Okay, and just with n equals 4, the notion of winding is a three-dimensional notion of winding. So now I have I have 4 vectors, right? Well, the 4 vectors are projectively in P3. We talked about projective geometry. So now I have a collection of 3-dimensional vectors, and this collection of 3-dimensional vectors winds around the origin in a 3-dimensional sense, some fixed number of times. Okay, so you just uplift this story the only way you can. We have nothing at our disposal, no dynamics, no time, nothing at our disposal other than these combinatorial and topological ideas. Okay, so you ask for that to be the positive part. You do exactly the same for the subspace, and the intersection of that subspace with the positive part gives you the amplituhedron. Okay? And now you see the amplituhedron directly in the kinematical space. And the final comment I'll make is that you're supposed to get a differential form in that space. Now, how do you interpret that differential form? It turns out that these dz's actually give you the helicities of the particles directly. So you would take this form. It has a piece with dz, this dz, another dz. Whichever number of dz's that it has, what multiplies that piece of the differential form actually gives you a particular helicity amplitude. It tells you what the helicities are. Okay, so the forms are a way of summing together all the helicities into one object. In fact, it's a supersymmetric theory. If you know anything about supersymmetry, you're supposed to be Grassmann variables somewhere. Where are the Grassmann variables here? There's no Grassmann variables anywhere. It turns out that these dz's of these differential forms are the Grassmann variables. Okay? You want to have anti-commuting variables? The stupidest way to have anti-commuting variables is to have them be differential forms, be differentials. And in fact, the form that we get in this way is literally the super Yang-Mills super amplitude, but with no super anywhere. I mean, the super is replaced by the dz. Okay? Okay, so that's the analog of the story. You see, it's extremely similar, but the kinematic space is different. And if I just come back to say one final comment about the association, then we'll go to lunch. You can ask, what is the meaning of the form in this context? So I just told you there's this funny form. There are these ds's. there's this form, and then I'm supposed to pull back to get the amplitude. But it was not clear what these DS's mean in this context. In the n equals 4 super Yang Mills context, I told you that they are about helicity. They actually combine and encode helicity. It turns out in this context, but I won't talk about this more, but in this context, all of these DS's are actually about color. It should sound a little mysterious, because we're talking about just one color ordering, blah, blah, blah. But it actually turns out that the DS's are objects that satisfy identical identities to color Jacobi factors. And if you go beyond the planar limit, you can take all of these forms for one ordering, add them up for all orderings. You'd have a form that now doesn't know anything about planarity, but everything is dressed by the DS's, which are the propagators for arbitrary graphs in arbitrary ordering. And those DS's are secretly color factors. You can take for any diagram, for any cubic diagram, you would write down as a color factor F, 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 F. We would instead also write down DS, 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 DS. And it turns out that those DS, DS, DS's satisfy identical color Jacobi relations to the color factors. And there's a canonical way to take the DS, DS, DS's, take them out, and replace them by F, F, F. So you go from these things to the fully colored amplitude. On top of that, let's say you don't want to do the color amplitude. Let's say you wanted a particular partial trace. You see, what I was talking about here takes you to a subspace, right? We have to go to these subspaces to satisfy the equation x plus x minus x minus x. Right? So we can write those equations in this larger kinematical space that has as variables all of the Sij's. I choose this subspace for any ordering that I like. I take this giant form, I pull it back to the subspace associated with a given ordering. Only the answer for that ordering survives on the subspace. Okay, so the DS's actually are all about color for this theory. Even though we haven't seen it really here at all, but you see that it has something to do with color when you talk about all orderings. Okay, but anyway, the last 15 minutes was purely impressionistic comments, but just so you have some idea of the slightly larger world in which these things live. Okay, let's go to lunch.